Hello everybody. In this video we're gonna solve one other example, or the second example in the textbook, which is similar to the previous one, with one important difference, which is very important to demonstrate the difference between the graphical solution and the numerical solution, and when it's easier to use either one of them. So this is a gas absorption process, which is the opposite of stripping, which we did last time. So the flow is going from the gas phase to the liquid phase, and we're removing ammonia from a mixture of ammonia and air using liquid water as a solvent. So we have ammonia transferring from gas phase to water, or from air to water. And the bulk gas stream contains 30 mole percent ammonia. The bulk contains 5 mole percent ammonia. So again, I'll highlight the parts that are important for us. So first, it's a gas absorption. So this will have like an important meaning for us to demonstrate or understand the direction of the flux. The next is the mole fraction of ammonia in the gas stream, which is Y, YA, and then XA is 5%, which is 0.05. And we have here the equilibrium distribution, which is here between gas and liquid phase at 30 degrees Celsius and 1 atmosphere total system pressure in mole fraction coordinates between XA and YA is displayed in the table. And this is the main difference between this problem and the previous one. In this problem, we have the equilibrium data as tabulated data. It's not equation or a linear relation as it was before. And this is a very common way of representing the equilibrium data, which is produced from experimental from experiments. So you do experiments and you get the results, and from the results you have them as table. You can get an equation that describes or fits with this data well, or you can just use the data as they are. And in this case, we have just the data as tabulated data between XA and YA, or the equilibrium data between XA and YA. We have here the mass transfer coefficients in the liquid phase and the gas phase, and we need to calculate the flux, the overall mass transfer coefficient, and the relative resistance in the liquid phase. So if you take a look at this problem with the inputs that we have, you would see that all the inputs are in the units of mole fraction. So I don't need to do any unit conversion as we did in the previous problem. But in this case, we have a challenge which is related to the equilibrium relation. So we don't have it as equation, we have it as tabulated data. And in this case, the easier option, we can do the solution numerically and analytically, and I'll do both. But the easier way is to use the tabulated data as tabulated data as they are. So to use the graphical solution. So if we want to start the solution, we have this the profile. We have the higher concentration in the gas phase, and the lower is in the bulk in the liquid phase. And these are the information that we have: the pressure, temperature, XA, YA, and KX and KY. What we are going to do is simply to plot the data that we have, which is just relation between XA and YA. Y is on the y-axis, XA is on the x-axis, and just to solve it graphically, so to do the graphical solution, we need to find the first point on the mole balance equation, which is PA and CAL, or YA and XA. And I know YA and XA. YA is 0.3 and XA is 0.05, so it's gonna be somewhere here, which is this point, XA and YA. And we will draw a straight line that passes by this point and has a slope of negative kx over ky. And we talked a lot about how to draw these lines. So if you draw the line, it's gonna look like this. And again, I'm repeating this again and again. You have to do this yourself. You have to do the drawing yourself. You have to draw the scale. You have to go through all these steps, because there are a lot of like things that may cause mistakes, so you have to try it yourself. Anyway, so the intersection of this line and this equilibrium curve is gonna be the interfacial concentrations, which is x interface is 0.099 and y interface 0.155. So these are the interfacial mole fractions. and we can get x star and we can get y star. So x star is gonna be 0.16 and y star is gonna be 0.065. So we have all what we need to get from the graph, and the rest of the calculations can be done simply without the need of the graph. So this is all what we need to get from the graph. We can do the same or get the same output by doing the solution or solving numerically, but the numerical solution is going to be challenging because we have to have the information that we have about the system in forms of equations to solve the equations numerically. So what we need to do is to do data fitting to get the equation that describes the equilibrium data that we have to describe it efficiently. And luckily we could get this by setting the or by using a second order polynomial equation, which is this. And I just want you to think of this step if you are doing this manually. This I could do this very simply because fitting is easy using Excel, using MATLAB, using any software that can do data fitting, and it was very simple and straightforward. But if you want to do this manually, it's gonna be very tough. It's very time consuming. So if you are doing these solutions manually, then the easier way or the easiest way to do this is to do this graphically. So this is the equilibrium relation, and now we have the mole balance equation, which is ky multiplied by ya minus y interface equal kx multiplied by xa minus x interface. And now we can we have this equation as one equation in two variables. We can substitute with this equation here. So this is gonna be y interface, which is this. Okay, so the y interface is a function of x interface, and it's now an equation that we can simplify to be an equation of second order polynomial equation in one variable, which is x interface. So we'll have two outputs, which is xa1 xa2 interface, which is negative and positive. So the negative is not like a valid result. So the valid result is this, which is exactly what we got from the graphical solution. And we can get y interface from the equilibrium relation, which is 0.1535. And again, we can now calculate the flux. We can calculate y star and x star from the flux or from the equilibrium relation. So I can calculate y star now, and so this is y star, and we can use this data to calculate the overall mass transfer coefficient. So now we have the flux already here. And this is one thing that we discussed before, that when you have a linear relation, you can use the equations that we have before as 1 over k overall equal 1 over kax plus 1 over hkg, or whatever the equation, if this is a linear relation. But if it's not a linear relation, it's not possible to use this equation. It's wrong. So it's not right to use these equations because you're using an equilibrium relation that doesn't fit with the equilibrium data that you have. So you have to use the option that we mentioned, or the method that we mentioned, which is simply putting the mass transfer in terms of overall mass transfer coefficient equals to the flux, which you calculated from the individual mass transfer coefficient. So this is, you have the flux, you have it equal ky multiplied by ya minus y star. So we have only ky, which is the unknown piece of information here. So you can now calculate ky as a function of flux and the mole fractions y and y star. And then you can calculate ky, and from ky you can get the overall, or the relative resistance in the liquid phase, which is going to be ky overall divided by ky individual, which is going to be 64, almost 64%. So I want to, so there is nothing special about this problem except for the use of the graphical solution. I just want to stress on this point because in the majority of the cases that we face, we have nonlinear equilibrium relations, and in many cases we have tabulated data. So dealing with the tabulated data numerically is not easy, and I insisted on doing this numerical solution to show you that it's gonna give the same result, and to show you how difficult is it to do it compared to the graphical solution, which is gonna be just intersection of two lines. It doesn't matter if it's linear or non-linear, it's the same thing. So I hope this point is clear, and I'll see you in the next video, inshallah. Goodbye.